NASA has just confirmed that an exciting new cosmic milestone has been reached. Over 5,000 exoplanets have now been discovered. So let's take this opportunity to talk about how we actually find these strange and distant new worlds. An exoplanet is a planet that's orbiting a star that isn't our sun, a world in another solar system. Just a few decades ago, we didn't even know if any planets existed beyond our solar system. But throughout the years, our searches have finally bore fruit, and the accelerating pace of the discoveries has now resulted in over 5,000 known exoplanets. This doesn't include the planets in our own solar system, so that's another 8. Yeah, I said 8. To add on if you want the full number of known planets so far. These planets come in all shapes and sizes, all temperatures and compositions. Some are rocky planets like the Earth. Many even have atmospheres that might be breathable, while others are super Jupiters, enormous gas giants whose surface temperature can be hotter than a star. Planets that aren't like any seen in our solar system have also been detected, including enormous Earth-like planets much larger than the Earth, or small puffy gas planets like Neptune, but much smaller. As I said, the announcement of new exoplanets are now coming pretty rapidly. On March 21st, 2022, we got the announcement of 65 new confirmed planets, and that took us over 5,000 known exoplanets, to 5,005 in fact. And it was only the previous day, March 20th, that we received the news of the batch of planets right before that. Almost all exoplanets, even the largest of them, are much too small and too faint to be directly imaged by even the largest and most powerful telescopes we have available. The best we have are artists' impressions of what we think these worlds will look like. Note that I did say almost, and I'll come back to that point later, so stay tuned. But if we can't see these planets through a telescope, how have we actually discovered them? There's actually quite a few methods for this, so let's just talk about the ones that have resulted in the most discoveries. The transit method, the radial velocity method, microlensing, and a few direct images right at the end. Let's start with the transit method. This is by far the easiest of the methods, and it counts for about 76% of all exoplanets discovered so far. This works by picking a star, any star, and you see how bright that star is, and then you just watch it for a long time. The idea that if an exoplanet is orbiting that star, and its orbit is in the right plane, it will pass in front of that star at some point and block some of the light, and we'll see the overall brightness of that star dip. As the planet then carries on around the star, the brightness will increase again. As this continues again and again, we'll see these dips continue on a regular basis. And this will tell us how fast the planet is orbiting that star. The amount that the brightness dips also tells us something about the size of the planet and the distance it is from the star. Although there is some degeneracy between those two properties, meaning we know something about the combination of those two, but we don't know them individually particularly well. As always, this method has its pros and cons, but in general, the pros do outweigh the cons, and this is why it's the method used by the main exoplanet hunting telescopes. The current NASA mission is called TESS, and this replaced the older Kepler telescope, which went offline in 2019. Between them, they've been incredibly successful at finding exoplanets. The pros are that this is a pretty easy method. Just watch a bunch of stars over time and monitor their brightness. The cons are that it's a very scattergun approach, just picking random stars and hoping they have an exoplanet or two. For example, the Kepler telescope looked at around 200,000 stars for years in order to make the discoveries that it did. Another con is that Kepler could look at a star with loads of exoplanets and see absolutely none of them if they're orbiting the star in the wrong direction. Also, if a star has multiple exoplanets around it, then the dips as the various planets orbit can get confusing as they will overlap. But by watching for long enough, the teams working on this can eventually work out the number and the orbits of the planets. The second most popular method for finding exoplanets is called the radial velocity method. And in fact, in 2019, half of the Nobel Prize went to Meyer and Queloz for their discovery of an exoplanet around a star that was pretty similar to our Sun using the radial velocity method. This was done back when there were almost no known exoplanets, and it represented a remarkable discovery since it was the first exoplanet discovered in a system that theoretically could have looked quite like our own solar system. The basic idea of the radial velocity method is that a planet doesn't really orbit a stationary star, but rather the two objects orbit each other around some center of mass, meaning that we can actually see the star oscillate back and forth, telling us that there's a planet orbiting it, giving it a regular tug and causing it to wobble. We measure this wobble by looking at the star's light and seeing if it's slightly redshifted or blue shifted in a repeating way. And this tells us the star is slightly moving away from us or towards us with the wobble. The speed and the amount that the star wobbles tells us how massive the planet is and how fast it's orbiting the star. Finally, the other significant method is called microlensing. This is based on gravitational lensing, which I've described in more detail in other videos. So here, I'll just say that because of Einstein's gravity theory called general relativity, heavy things warp space. This method does need another star in the background of the star and exoplanet you're about to discover. If the lensing star passes in front of a background star, it will bend the nearby space a little bit, causing the light of the background star to take a slightly different route to reach us. And this actually causes that star to look a little bit brighter than normal. I say little, but sometimes the effect can be quite large, even up to a 1,000 times increase in brightness, and it can last for weeks or months. If the star doing the lensing has an exoplanet orbiting it, then the planet can add to the lensing effect, and we see another peak in the brightness of the background star. This extra lensing typically lasts for a few hours or a few days, and this method is especially good at finding very distant exoplanets, which the other ones struggle with. It's also much better than the other methods at detecting even low mass exoplanets, possibly even down to masses similar to Mars in the future, while the other methods we discussed are much more effective at finding very massive exoplanets. It can also be used to find exoplanets with wide or long orbits, like Saturn or Uranus in our own system, while the other methods tend to see many more planets on fast orbits, simply due to the frequency that they transit or wobble their parent stars. The disadvantages of microlensing as a detection method are the fact that it can only place loose constraints on the mass of the planet, and it can't tell us anything else at all about what the planet's like or its orbital period. And also, it's completely unrepeatable. The lensing events are one-offs, and while the other methods can be seen to repeat if you watch for long enough, this can't happen again, and it means that follow-up work is almost impossible. You might now, as I did, wonder why a planet transiting its star is commonly detected by causing a dip in the light it sees, and why it doesn't lens the light and actually increase the brightness like we've just seen here. Well, it turns out that when it's just one planet in front of one star, the planet is too close to the star to cause significant lensing, as well as the apparent size of the planet being too small as well. And therefore, the dip in brightness of the planet blocking the star is much more significant than any lensing in this configuration. You might remember at the beginning of the video, I said that almost all exoplanets are currently impossible to see directly with telescopes. I actually found out while reading up for this video that there are a few exoplanets, 14 at the moment if you want to be precise, that have been detected with direct images. This is incredibly difficult to do because planets are incredibly faint and their small amount of light tends to be washed out and lost in the glare of their parent star. It is possible though, if the planet orbits far enough out from its star, it's close enough to our own solar system, and if the planet is nice and big. It also seems from my research that the images tend to be taken in the infrared wavelengths of light, where the planets tend to be brighter than they are in visible light. And the telescopes are usually aided with what's effectively a sun shield that blocks out some of the light of the parent star. However, even with all of this done, the images are somewhat blobby, shall we say. They aren't as crisp as we might hope, but remember, this is a planet orbiting a different star, and to me, these images are still mind-blowing. Finally, let's end by taking a look at this amazing Kepler orrery, showing some of the many exoplanets discovered by the Kepler Space Telescope. It shows every multi-planetary system that Kepler discovered, and it's even color-coded to show us the temperature and scales of these orbits. Although, do note that the sizes of the planets aren't to scale. This is because the smaller ones would be impossible for us to see if that was done. Even though we don't have detailed, direct images of most of these planets, in the near future, the ever-impressive and ever-popular James Webb Space Telescope will soon peer into the atmospheres of some of these exoplanets. It will look for chemical signs of life in these atmospheres, and I have more details about that in a video I made before about JWST right up here. Also, take a look and listen to this incredible video from NASA showing us over time the locations of the known exoplanets. They even added some musical notes for each planet so we can hear as well as see the accelerating discovery pathways for all of these brave new worlds. I'll have a follow-up video to this one that's looking at some of the craziest and most amazing and unbelievable exoplanets that we've discovered so far. Subscribe so you don't miss that, and you'll also get loads of other astronomy and astrophysics videos on the channel too. And leave a comment below if you have a topic that you'd like to see me cover. Until next time, stay safe team. I'll see you soon. Bye!